All right. Now, as we go through this, we are continuing on a little bit today with the rational zero test. How do we find the polynomials? It's P over Q, and I call them PQ lists. Where do P and Q come from? Kidneys and?
Toes?
Well, P comes from your kidneys, right? All right, but P and Q with regard to factoring stuff, what's P? Factors of the constant, the thing at the very end, and Q are factors of the leading coefficient. Now, there are times in here, and we're going to see a new rule today, and we'll just make sure that we can kind of make sense of it. It can be really wordy, but we're going to introduce just a little extension. Our overall thing is a rational zero test, right? That's the bullet point that we're in right now. Okay, so as a subsection within the rational zero test, we are going to discuss some of the work of René Descartes, who is responsible for the Cartesian plane. It's that guy. And we're going to talk about Descartes, and he's French, so it looks like Descartes. Descartes, and Descartes specifically, rule of signs. Not the sign function, but S-I-G-N, like positive and negative. Descartes' rule of signs. Now, to be completely transparent, you could get by with never doing this. It's possible. Now, my job is like I've taught you how to do the math, but this is super duper helpful for being a little bit more efficient. If I have a list of 500 things to check and they're all plus and minus, that's a huge list, right? So if I went into a problem knowing that there weren't going to be any negative roots, that would be super helpful because it literally cuts my list in half. Do you guys agree with that? Okay. The benefit in doing that, if you guys can see value, it is exactly in Descartes' rule of signs. And it's kind of wordy if we write it all out. I'm going to try to be less wordy, and we'll see if it makes sense. So before you write it, let's talk about it first, and then if it makes sense, we're cool with it. So for this, given a polynomial function, and you can write this, given a polynomial function, we, like Descartes figured this out, we have a way to see the number and types of zeros we expect. The number and I'm going to say sign of zeros. Okay, so that statement, nothing's too crazy there, I don't think. If I give you a function, we're about to see that there's a way to see that if I have 4 roots, maybe 2 of them are positive and 2 of them are negative. Or maybe 3 of them are positive and 1 of them is negative. Like that would be useful information for me to break down and make my search more efficient. Okay, the way that we determine this, and we're going to write a table, and when we do it, we're going to make a small little table that says the positives, the negatives, and the complex. Okay, where we should say imaginary, but I'm just going to use complex to indicate that we're talking about the imaginary stuff. Okay, when we do this, I'm going to say it first and see if it makes sense. If I said the number of sign changes in the function f, and I'm going to write one here. We'll do an example, and we'll do the same example, but I'm going to write it first to see if we can make sense of it. If I give us this, x cubed minus 3x squared plus x plus 1. If I asked you, how many times does f of x change signs? How many do you notice?
2.
I hear 2 and I hear 3. Well, let's check. Walk me through. Do we all agree the first one is from a positive 1x cubed to a negative here? We change from a positive to a negative. When I go from here to here, what do I change from? A negative to positive. If I go from here to here, I'm from positive to positive. Did it change? Okay, so when we say how many sign changes, how many do we just count? 2. If I write out our theorem and say, or our rule, I say the number of sign changes of f of x, is this going to be immediately clear that this is what we're talking about? And if it's not, when we do an example here in a second. Okay. So for this, we are going to organize this very differently than I have in the past because I think it'll make sense, and I hope it does. But if it doesn't, you're going to do what? You're going to tell me. So when we look at this, we're going to say the possible, and we're going to have 3 different pieces, the possible positive zeros. And I'm going to say possible number of positive zeros. Sorry. Now, I will never really write it like this again, the possible number of positive zeros. The way that I shorthand this is I'm just going to say it's R plus. That'll be the notation that I use. That's a positive real number. Okay, when we want the possible number of positive real zeros, here's our statement. It is the number of sign changes of f, the number of sign changes, and I'm going to be really specific, this number of sign changes of f of x. And we're going to pause here because then I'll go back to that pink example and we'll make sense of it. On that one, we already decided it's how many? 2. Now, if I said or less than that by an even number, that's a weird phrase, but it's, I think, the easiest way you can write it. What's an even number? 2 or 4 or 6, right? So if I know that there are 2 right now, and we'll do an example. You don't have to write anything in pink. But right now, if I'm just using what I have, the possible number of positive real zeros could be 2, because I counted 2 sign changes. Or less than that by an even number. Do you guys understand what I'm saying there? Or, and thank you for your honesty. What's the first even number? So let's try to take away 2. Could we take away 2 from this? So careful. 2 minus, let's just start taking away an even number. 2 minus 2 is? 0. Now, I could take away 2 again, right? But now it doesn't make sense. Is it possible that there's 2 positive roots? Like, is that a reasonable thing to say? Is it possible that none of them are positive numbers? Sorry, those are all positive, sorry. There's a graph that has 3 negative roots. None of them are positive, right? Yep. Is it possible to have -2 positive roots? Like you can't have -2 of something literally, right? Okay, so if we don't like the language or less than by a even number, my alternative would be the number of sign changes of f of x, or an even number less. Like I'm trying to think of how I would word this if I'm changing it. Because I've always said or less than that by an even number, which it might make sense now. Can I write that? Or an even number less than that. And we'll get practice with this because the wording is clunky. Okay. I don't like that one, but that's okay. The book literally says less than that by an even number. Like it's how they word it, and it's clunky and it's awkward. You could do minus 2k, where k is a number. Like there's a million ways you could write it. We'll get practice. Now, we have the possible positive zeros. That's a huge help. Because if I know there's none of them, that's pretty handy. I won't check any positives. There is another side of this statement. Excuse me. We also have the possible number of negative roots. I'm just going to use pos for possible. Number of negative roots. Or zeros, if that's what we used. Okay, for the possible number of negative zeros, any suggestions on how I'm going to denote this? Real numbers? Negative. Okay, for this one, it is going to be everything the exact same with one minor change. We are going to look at the number of changes and the number of sign changes of f of negative x, or less than this by an even number, or an even number less. Okay, this is it. This is going to allow us to conceivably, and it won't always happen, but if I have a huge list and I have, again, 50 numbers and plus and minus, if I can get rid of half of them, I'm going to literally cut down half the work. Because in the worst case scenario, where it's not until the very last term, we would have to do up to 100 things. I don't really want to do 50 things either, but I'd much rather do 50 of them than 100. Okay, literally half the work. Okay, there is a third place sneaking around here, but it's not related to Descartes. Let's do some practice with this. Okay, we're going to do a problem where we immediately implement Descartes' rule of signs, and we'll make sense of it together, and then we'll recheck the PQ list to make sure we can do all of it together. Okay, If you're uncomfortable with it now, real quickly, who feels like this is going to be like you're not really quite sure and this feels like it might be hard? Okay, I'm going to ask the same question in about 5 minutes. I want honest answers. If it's still hard, please tell me. If it's not, please tell me. Let's do an example. I want us to solve, but we're going to specify this time, use the rule of signs. Not to be confused with the law of signs from geometry. This is not the sign function. This is just sign like parity, positive, negative. Okay, so let's find one that works really nice here. All right, so on this one, and I try to do the examples that aren't the exact same as the book. Here we go. So on example A, we have the following polynomial. I want us to work with f of x equals x to the fourth plus x cubed plus 3x squared minus 1. Okay. Now, right off the bat, couple big questions. How many zeros are there?
4.
There. Ooh, love it. Why 1, out of curiosity? So you heard the question as how many x to the 0 powers are there, which I agree. There's just a 1. But just in general, this is a 4th degree polynomial. I know that there will be 4 roots. And maybe I should have asked for roots because I can see the ambiguity. Okay. Now, these numbers are going to be super easy to check, and maybe this was not a great example to check with it, but there is some good practice that we can do. If we're using Descartes' rule of signs, and again, I want to stress, this is really and truly optional, but it is a huge benefit to use. I'm going to leave an awkward gap very intentionally, and I'm going to make a little table. I'm going to put an R plus, and then I'll switch color just so we can tell them apart. I'm going to put an R negative, and then there's really only one other option. With the exception of if x is 0, it's neither positive nor negative. My roots can either be real or they could be complex. So your book, I've never seen anybody else do it this way. This is a Holloway notation, but it has seemed to work really well over the years. So I'm going to use this. Okay, let's do it to it. Notice this awkward space that I left. We'll even make some comments. If I want to know the number of positive real zeros that could possibly show up, what's going to happen is I'm just going to count the sign changes. So you guys are just going to help. From this term to this term, did we change signs?
No.
Nope. How about from here to here?
No.
Nope. How about from here to here? Yes. How many sign changes did we just count?
1.
So what we see now is it could be 1 or less than that by an even number. And all that really means is I start taking away 2 until I can't anymore. Can I take away 2 from this and have it make sense? No. And check out what just happened. I guarantee then that there will be a positive root, which means when I started generating my PQ list, do I have to check any negatives? It's going to be a positive. That's what I'm going to start checking. I've already cut off half the list, but this also serves more than just cutting off half the list. I guarantee there's a positive. Now, there might be some negatives, but if we can find the one positive and divide, we're going to get the other ones out of it.
Oh.
Yep, like we just cut off half the list, but there's even more to this. We can use this to check our answers, right, Leigh? Will you go get me a drink real quick? I'm super thirsty. Cool. All right. Yeah, that's also fine. I have to pee too, so you're in luck. All right. This one is a little bit harder. Here is what I want you guys to see if you can come up with how I do this. We also need f of negative x. Now, here's the cool thing. Do I ever tell you that I worry about the numbers that are here or just the signs? Just the signs. I don't care at all about the numbers. Now, you certainly could actually plug it in and try to evaluate it, but here's what I'm going to suggest. If I'm plugging in a negative x, and it's to an even power, so negative x to the square, or to the 4, or to the 6, if you take a negative and you square or 4th or 6th power it, what happens to it? It turns into a positive. The sign would change from negative to positive. What if it's an odd exponent? It would stay as a negative, right? So I'm going to use that. And this is the part where if there's questions, whether you're watching this live in class or on a video, if there's questions, please reach out. If I plug in a negative x to this, is it going to be a positive x to the 4th or a negative? Positive. I don't even care about the number. I just know it's going to be positive. What if I plug in a negative x into this one? It would be a negative x cubed, right? Now, what I'm not writing is really all of that. I know that it really and truly would be x to the fourth minus x cubed, but I don't care about that part. I just care that it's positive and a negative. How about this one? It's positive now, and if I did it, it'd stay positive. And this one, is there even an x to plug in? So no matter what I pick for x, it's going to stay negative. We don't actually have to find f of negative x. I just need to be able to think about what happens with the coefficients. If it's an even power, it stays the same. So whatever the sign was, it would be the same. If it's an odd power, we just change it. Now, this, I think we can count. How many sign changes do you guys see here? One there, right? One. And then negative to positive and positive to negative. There are 3 of them. Or less than that by an even number. So I'm going to start subtracting 2 until I can't anymore. It could be 3 or it could be 1. Now, coincidentally, we have just now guaranteed that there will be at least 1 positive, because that was the only possibility, and there will be 1 negative. Okay, here's the weirdest part, and I wish I could cover this up and show it on the camera. Yes? So are you okay with the 3 sign changes? 1, 2, and 3? Or less than that by an even number, I just start taking away 2 until I can't anymore. Okay, so like had this been 7, hypothetically, I would have been 7 or 5 or 3 or 1. And I just count down by 2 until I get to 0, because I can't go beyond 0. Okay, thank you for interrupting. Appreciate it. That wasn't an interruption. Thank you for the question. Okay, here's the weirdest part. Your book, and I've never, again, I just want to stress, I've never seen any book reference this. How many roots total?
4.
We know there's 4. Now, I'm going to consider the possibilities. Right now, it is a possibility. It's not a guarantee, but 1 is positive and 3 are negative. Do you guys agree that that's one of the possibilities? So I'm going to turn on the camera, and actually I'll just use this because that'll work. Because I do this every time, and it's strange, but I just want to make sure that, like, in my head, whoa. Cool. All right. On this problem, and I'll try to move it over so we can all see it, but I do want it to record as well. Okay. I'm just going to hold up my hands. I know there's 4 total because it's a 4th degree polynomial. One of them is positive, right?
Yeah.
And then how many of them could be negative?
3.
How many of those zeros have I used already? If I know there's going to be 4, how many have I found?
3. 4.
There's 4 total, right? 1 positive plus the 3 negative. I have 4 fingers up. There's 4 roots. In that situation, how many of them would have to be complex? 0. Because if I have 1 positive and 3 negative, I've used up all 4, and I know that there are exactly 4 because it's a 4th degree. There's no room left to be a complex. But if instead it's this other situation where it's 1 positive and 1 negative, because that was the other option, I've only used how many?
2.
Which means the other 2 must come from here. It could be 0 or 2 complex. Now, the other day when we did here's the roots, and notice that they always come in conjugates, we're seeing the same idea right here. Complex roots always show up in pairs of 2. You are never going to have a 1 written here. It can't happen. If you have a single imaginary root, you're guaranteed 2 because it would have come from the quadratic formula, and you have to have the plus or minus version. You will only have even numbers right here. Okay, now, in reality, this saved a little bit of time on the get-go. Let's go ahead and run through it. What numbers are we going to check? So now we'll just run the problem like it was yesterday, and now we'll review from there, and we'll confirm with these at the end. So help me out here. I want to start listing out my possible rational roots. Where do I find them? Good. Factors of the constant?
1.
And factors of the leading coefficient? 1. Now, in reality, maybe Descartes didn't really hook us up on this problem, right? There's only 2 numbers to check. Now, in this case, it doesn't matter. There's no chance that I have 0 that are real. So I would check 1 and negative 1. I'm going to try 1, and without a calculator, I think we can check it. It should give me a 0 if it's a root. What's 1 plus 1 plus 3?
4.
1 plus 1 is 2, plus 3 is 5, minus 1 is 4. Was that 0?
No.
Okay, let's try negative 1. Negative 1 to the 4th
1.
is 1, minus 1 is 0, plus 3, uh-oh, Minus 1. Okay, so here's the deal. I picked a terrible problem. That's okay. We're going to scratch that part, and we'll do a real one. This was just the Descartes rule of science practice. I just, like, all this problem said is describe the possible real zeros. It didn't say actually solve it. That's my bad. Let's do one where it actually makes sense to use Descartes.
Where'd you get 0 and 2?
Okay, love it. Are you okay with, I'm going to change this instead. How many zeros do you guarantee this function has? 4. Are you okay with how we got the 1? Okay, so check it out. I'm going to make you physically touch my hand. It's weird because I usually don't touch people. Here's the one positive. How many do we say could be negative? So I'll actually touch it because it makes me kind of cool. How many fingers do I have up? And how many, so these are my roots, right? How many do we say we're going to find? If I found all 4 of them, how many can be complex?
All 0.
If it was 1 positive and 1 negative, I found 2, and how many are left that must be complex? There it is. Yep. Cool. All right, let's do a real problem here. One that works. Oh. Oh. Okay, here we go. I don't think we did this one. This one we actually will be able to solve. That's my bad. Sorry for the bad problem. In the case that you can't solve it, we don't have options in here. I won't give you one to solve that you can't. All right, so here we go on B. I want us to solve using the rule of signs all the same. G of x is equal to x cubed minus 3x squared plus 7x minus 5. Should we do this whole one together? Or do you guys want to try the Descartes thing on your own first? Try it on your own. I will always, in my notation, leave a little gap here because the very first thing that I would do is think about the signs of negative x. I can write that better, I suppose. And I'm just going to give you guys a minute. I'm going to build my little table, r plus, r negative, and complex. And we'll meet up here in just a second. And I actually will ask for one of them. How many sign changes on the original g of x? 3. So there could be 3 positive roots or 1. Everybody get that same thing? Now, I cannot stress enough, and I might even write this down. If odd, power, when we do the g of negative x, if it's odd, change sign. The sign will change if it's an odd exponent. If even, don't change. And I'm not going to write that one. So check it out. This is an odd exponent or an even? Odd. And if I do negative x, it changes sign. So now it'd be what? Negative x cubed. The next one is negative to begin with because it's negative 3x, right? And if it's even, the sign does not change. What is it still? Negative. If you're uncomfortable with it, check it out. I'll even do it here. I'm trying to get us to skip this is really all I'm trying to do. Because I think that we can do it without this, but maybe the first time it's nice. Just to show you that it stays negative. Is everybody okay with this one? Is negative x times negative x times negative x is indeed negative x cubed. Okay, and I'm doing this one, right? If we evaluate this one, what's negative x squared? X squared, like it turns positive, right? Times a negative 3 is now a negative 3x squared. Don't even care about the 3x squared. I care about the negative in front. If it's even, the sign stays what it was. If it's odd, the sign changes. This power is odd. Does it stay the same or does it change? It was positive. Now it's negative. This one doesn't have an x, so it doesn't ever change. Negative. They're all negative when we do this. And if you want to go through and add x cubed, 3x squared, and 7x, and 5, you can. But all those last 4 things that I added aren't necessary. We don't need them. Cool. How many sign changes do you count? Am I going to check any negative numbers? No, I've literally removed half my list when I get there. Okay, hardest part. How many total roots does this function g have? 3. Could it be 3 positive and 0 negative, and I've used all 3? Yes. No, I don't have the camera up anymore. So check it out. If I do 3 positives, I'm going to put up, here's my 3 positives. And there's only a choice of 0 negatives, right? So these are the 3 that I have. How many total roots are there? And if they're all three positive, how many of them can be complex? 0. Or it could be there's 1 positive and 0 negative, which means I need how many more in the complex to get to 3? 2. These are all the possible combinations. Now this problem will actually work. I don't do this for 2 reasons. 1, you don't need it. 2nd, I can feel myself about to make a mistake as I'm trying to figure out what I'm plugging into. If I don't have another function written, I can't try to plug into it. Cool. All right, so now we can actually do this problem. And help me out here. How do I find the possible roots? Possible rational roots anyway. Plus or minus something. So P, factors of 5. 1 and 5. Factors of this term, right? And the leading coefficient is a 1. Now, I'm going to claim that I've done even more than I needed to. Is this ever going to happen? So, no, you're good. This is factors of 5. And these are factors of 1. P over Q. Now, I didn't really need to write plus or minus. It's a habit. There's no negatives. I guarantee there's no negative roots. We see that there won't be. Descartes rule of signs. So it means we really only have 2 numbers to check, right? It's either going to be 1 or 5. Use either your brain to evaluate it. If you want to, 1 is easy enough to do there. I think 1 works. You can use your calculator to verify. When you do 1, I don't think you need to. Let's try to plug in 1 and see if it spits out 0. What's 1 cubed? 1 minus 3. Negative 2 plus 7? 5 minus 5? 1 works. Like, I can see x equals 1 is a root of this. So, what do we do with it once we find it works, whether it's on our calculator or not? Let's synthetically divide it. And I'm going to pause here, and I'm going to let you guys continue on. Let's see if we can solve this problem from here on. I think you might have been able to solve it before, but we need practice with that part. Cool. I'll give you a minute. I'll come walk around and be nosy. Do it to it. So if we're doing this here, then the very next thing that we're going to do is we're going to run through the synthetic division and verify. So 1, 1, negative 2, 5, 5, and a remainder of 0. Now, easy to overlook, but at this point, what we have is g of x, my lovely function. I know that x equals 1 is a root, or alternatively, x minus 1 is a factor, and these are the coefficients of my other piece, or my other factor, I'm sorry. So it was x cubed, so now we get a 1x squared minus 2x plus 5. And this guy is prime, so we don't have to do anything else to this, but we should try to factor this piece down a bit. Unfortunately, I can't come up with factors of 5 that add up to negative 2. So I'm going to get a root out of this one, and I'll say, check it out, I already have a root is x equals 1. But then here we need our other roots, and if I can't factor it, to get those roots, I'm going to use the quadratic formula. Now, if you don't remember it, negative b plus or minus the square root of b squared minus 4ac all over 2a. And let's just go ahead and do this. I heard people saying, no, 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 the humanity, please don't, stop it. It doesn't have to be that way. If b is negative 2, negative b is 2. Plus or minus the square root. And let's see, b, or negative 2 squared, is 4. Minus 4 times a 1 right here, times c, which is 5. All of this over 2a. All right, and you're going to see a sudden change in the volume because I'm going to talk with everybody here. All right, so I'm going to catch up to you guys. Here's the quadratic formula, which you have to use. Now, looking at it, I do want to highlight, not to pick on anybody in particular, but somebody had an answer, and I went and looked at it, and I could tell that they were wrong. I couldn't see the mistake in the math. They were having trouble finding the mistake in the math, but I knew they were wrong because when they got to their answer, they had a negative root. There will not be a negative root, and if you find one after doing Descartes' rule of signs, it's a nice second check to see that something went wrong. I know that there's supposed to be 0 of them. Okay, I hear you guys doing a lot of talking about the quadratic formula, and I couldn't really tell if I was arguing or not because I was talking to myself up here, but this is, I think, what we should have. Now, I'm going to clean it up maybe more than you would naturally. This is 4 minus 20. That's negative 16. Okay, I'm going to take 2 steps when normally I would do it in 1. All over 2 still. Gosh, 16 is like taking a negative 1 times 16, right? Well, what's the square root of 16? And what's the square root of negative 1? I. So the square root is 4i. Now, if you want to clean everything up and divide by 2, we can. This looks like 1 plus or minus 2i. So notice, I'm going to write all these out. This was my first factor and root. It was x equals 1. Now, I made people write it as a factored form here. You really don't have to do this, but I do think it's nice to make sure we don't lose track of what's actually going on. Okay, this is the factored form, kind of. It's not completely prime, but it's factored nonetheless. Notice what we just found. I had x equals 1. That was from the get-go. And then over here, I'm going to write these answers as well. We had 1 plus 2i, and we had 1 minus 2i. That's what I'm claiming are the 3 roots. Now, if I wanted to be like completely 100% convinced that I'm correct, I could FOIL all of this back out or distribute it all back out, which we did this the other day, right? X minus 1 times x minus 1 plus 2i and x minus 1 minus 2i. And we did that whole problem. You can look back. I don't think we really need to do it again right now, but you could. But here's, instead of doing that, without being 100% convinced I'm correct, I can at least see some hints. We said there should be 3 roots in the beginning. Are there 3 roots?
Yes.
We said that of those 3 roots, there should either be 1 or 3 that are positive real numbers. Here's a single positive real root. That was on the list. Okay, we said that there should be 0 negative real roots. Are there any negative real roots? We also said that if it were 1 and 0, there should be 2 complex or imaginary roots. We found 2 imaginary roots. That is a ton of evidence to suggest that I'm correct without truly checking it and foiling and expanding everything back out. I'm convinced we have it. Okay, when we look at this, is Descartes' rule of signs as bad as it seemed?
No, not even close.
No. Is it ever required?
No.
Are you going to do it?
Absolutely.
Okay, and that's okay. There's both answers. I heard really emphatic yes, I will, and I heard an emphatic no. It depends on the problem, realistically, for me. If I have 4 numbers to check, I'm probably not going to take the time for it. But if I had 50 numbers to check, for sure. Okay. All right. This section is arguably one of the harder sections with like all the factoring stuff. Does it seem all right? I guess we'll find out because I'm about to give you an assignment and you're going to have to demonstrate that it feels either okay or not. Okay, so let's see here. Today's what, Thursday? And you guys want, Addison said she wanted 3 hours of homework tonight just to get all out of the way.
What?
No, don't listen to her. She never say that.
Dolan, you and I are on the same page here. Good.
No.
All right.
He's the outlier.
Page 164, I think. I don't know. Okay, sure. Let's get the assignment. So let's see. Today is, wait a second. Today is the 9th. I already did this. Look at me being productive. How many problems do we want? So how many problems do we need to be able to do it successfully is the bigger question. I want you to do 9, 10, 14. Whoa, 9, 10, 14. I should probably give you the page. What? Homework! Goodness, 2.5. You will find this on page 164. And I want you guys to do problems 9, 10, 14, 16. Yep, I see that now. 9, 10, 14, 16. 21, 22, 29. I always like it when I take like a 40 number jump, and I'm always curious to how good the problems are. 73. For real though. Well, hold on here. Let's just slower rolls. Oh my gosh, I kind of love it.
No, no.
Okay, the asterisks are around it for a reason. This last problem, number 112. And I think if I erase both asterisks, I can make it fit on the line before. Psych. What? Okay, eventually it will happen. Okay, the asterisks, whatever, are there. It's so frustrating on my end. I want you to try it. I don't know what the prize will be, but if you can do it and you get it right and you can explain it to me, which means you don't just find the answer on Calc Chat and look at it. If you can explain it and teach me as if I have no idea what's going on, I will buy you the drink of your choice over at V's. It's not called V's anymore, it's a Snack Shack.
Didn't Abby tell you about the schedule change with the podcast?
Yes. Cool. All right. 10 minutes. Cool. Have fun, Raiders. I hope you're playing well. I hope you're swimming well. I hope you're studying well. Baller.